A time series is a sequence of data points that 1. Consists of successive measurements made over a time interval. 2. The time interval is continuous. 3. The distance in this time interval between any two consecutive data point is the same. 4. Each time unit in the time interval has at most one data point. Examples of time series are ocean tides, counts of sunspots, and the daily closing value of the Dow Jones Industrial Average. Non-examples: the height measurements of a group of people where each height is recorded over a period of time and each person has only record in the data set. Panel data set is sometimes difficult to be differentiated from time series data set. One data set may exhibit both characteristics of panel data set and time series data set. One way to differentiate is to ask, what makes one data record unique from the other records? If the answer is the time data field, then this is a time series dataset candidate. If determining a unique records requires a time data field and an additional identifier which is unrelated to time, then it is a panel data candidate. If the differentiation lies on the non-time identifier, then the dataset is a cross-sectional dataset candidate. Time series are very frequently plotted via line charts. Time series are used in statistics, signal processing, pattern recognition, econometrics, mathematical finance, weather forecasting, intelligent transport and trajectory forecasting, earthquake prediction, electroencephalography, control engineering, astronomy, communications engineering, and largely in any domain of applied science and engineering which involves temporal measurements. Time series analysis comprises methods for analyzing time series data in order to extract meaningful statistics and other characteristics of the data. Time series forecasting is the use of a model to predict future values based on previously observed values, while regression analysis is often employed in such a way as to test theories that the current values of one or more independent time series affect the current value of another time series. This type of analysis of time series is not called time series analysis, which focuses on comparing values of a single time series or multiple dependent time series at different points in time. Time series data have a natural temporal ordering. This makes time series analysis distinct from cross-sectional studies, in which there is no natural ordering of the observations. Time series analysis is also distinct from spatial data analysis, where the observations typically relate to geographical locations. A stochastic model for a time series will generally reflect the fact that observations close together in time will be more closely related than observations further apart. In addition, time series models will often make use of the natural one-way ordering of time so that values for a given period will be expressed as deriving in some way from past values, rather than from future values. Time series analysis can be applied to real-valued, continuous data, discrete numeric data, or discrete symbolic data. Methods for time series analyses. Methods for time series analyses may be divided into two classes: frequency domain methods and time domain methods. The former include spectral analysis and recently wavelet analysis. The latter include autocorrelation and cross-correlation analysis. In time domain, correlation analyses can be made in a filter-like manner using scaled correlation, thereby mitigating the need to operate in frequency domain. Additionally, time series analysis techniques may be divided into parametric and non-parametric methods. The parametric approaches assume that the underlying stationary stochastic process has a certain structure which can be described using a small number of parameters. In these approaches, the task is to estimate the parameters of the model that describes the stochastic process. By contrast, non-parametric approaches explicitly estimate the covariance or the spectrum of the process without assuming that the process has any particular structure. Methods of time series analysis may also be divided into linear and nonlinear, and univariate and multivariate. Analysis. There are several types of motivation and data analysis available for time series which are appropriate for different purposes. Motivation in the context of statistics, econometrics, quantitative finance, seismology, meteorology, and geophysics. The primary goal of time series analysis is forecasting. In the context of signal processing, control engineering and communication engineering, it is used for signal detection and estimation, while in the context of data mining, pattern recognition, and machine learning, time series analysis can be used for clustering, classification, query by content, anomaly detection, as well as forecasting. Exploratory analysis. The clearest way to examine a regular time series manually is with a line chart such as the one shown for tuberculosis in the United States, made with a spreadsheet program. The number of cases was standardized to a rate per 100,000 and the percent change per year in this rate was calculated. The nearly steadily dropping line shows that the TB incidence was decreasing in most years, but the percent change in this rate varied by as much as plus or minus 10%, with surges in 1975 and around the early 1990s. The use of both vertical axes allows the comparison of two time series in one graphic. Other techniques include autocorrelation analysis to examine serial dependence, spectral analysis to examine cyclic behavior which need not be related to seasonality. For example, sunspot activity varies over 11-year cycles. Other common examples include celestial phenomena, weather patterns, neural activity, commodity prices, and economic activity. Separation into components representing trend, seasonality, slow and fast variation, and cyclical irregularity. See trend estimation and decomposition of time series. Curve fitting. Curve fitting is the process of constructing a curve, or mathematical function, that has the best fit to a series of data points, possibly subject to constraints. Curve fitting can involve either interpolation, where an exact fit to the data is required, or smoothing, in which a smooth function is constructed that approximately fits the data. A related topic is regression analysis, which focuses more on questions of statistical inference such as how much uncertainty is present in a curve that is fit to data observed with random errors. Fitted curves can be used as an aid for data visualization, to infer values of a function where no data are available, and to summarize the relationships among two or more variables. Extrapolation refers to the use of a fitted curve beyond the range of the observed data, and is subject to a degree of uncertainty since it may reflect the method used to construct the curve as much as it reflects the observed data. The construction of economic time series involves the estimation of some components for some dates by interpolation between values for earlier and later dates. Interpolation is estimation of an unknown quantity between two known quantities, or drawing conclusions about missing information from the available information. Interpolation is useful where the data surrounding the missing data is available and its trend, seasonality, and longer-term cycles are known. This is often done by using a related series known for all relevant dates. Alternatively, polynomial interpolation or spline interpolation is used where piecewise polynomial functions are fit into time intervals such that they fit smoothly together. A different problem which is closely related to interpolation is the approximation of a complicated function by a simple function. The main difference between regression and interpolation is that polynomial regression gives a single polynomial that models the entire data set. Spline interpolation, however, yields a piecewise continuous function composed of many polynomials to model the data set. Extrapolation is the process of estimating, beyond the original observation range, the value of a variable on the basis of its relationship with another variable. It is similar to interpolation, which produces estimates between known observations, but extrapolation is subject to greater uncertainty and a higher risk of producing meaningless results. Function approximation in general. A function approximation problem asks us to select a function among a well-defined class that closely matches a target function in a task-specific way. One can distinguish two major classes of function approximation problems. First, for known target functions, approximation theory is the branch of numerical analysis that investigates how certain known functions can be approximated by a specific class of functions that often have desirable properties. Second, the target function, call it g, may be unknown. Instead of an explicit formula, only a set of points of the form is provided. Depending on the structure of the domain and codomain of G, several techniques for approximating G may be applicable. For example, if G is an operation on the real numbers, techniques of interpolation, extrapolation, regression analysis, and curve fitting can be used. If the codomain of G is a finite set, one is dealing with a classification problem instead. A related problem of online time series approximation is to summarize the data in one pass and construct an approximate representation that can support a variety of time series queries with bounds on worst-case error. To some extent, the different problems have received a unified treatment in statistical learning theory, where they are viewed as supervised learning problems. Prediction and forecasting in statistics. Prediction is a part of statistical inference. One particular approach to such inference is known as predictive inference, but the prediction can be undertaken within any of the several approaches to statistical inference. Indeed, one description of statistics is that it provides a means of transferring knowledge about a sample of a population to the whole population, and to other related populations, which is not necessarily the same as prediction over time. When information is transferred across time, often to specific points in time, the process is known as forecasting. Fully formed statistical models for stochastic simulation purposes, so as to generate alternative versions of the time series, representing what might happen over non-specific time periods in the future. Simple or fully formed statistical models to describe the likely outcome of the time series in the immediate future, given knowledge of the most recent outcomes. Forecasting on time series is usually done using automated statistical software packages and programming languages, such as R, S, SAS, SPSS, Minitab, Pandas and many others. Also see statistical prediction, statistical inference classification, assigning time series pattern to a specific category. For example, identify a word based on series of hand movements in sign language. Regression analysis, estimating future value of a signal based on its previous behavior, e.g., predict the price of AAPL stock based on its previous price movements for that hour, day or month, or predict position of Apollo 11 spacecraft at a certain future moment based on its current trajectory. Regression analysis is usually based on statistical interpretation of time series properties in time domain, pioneered by statisticians George Box and Gwilym Jenkins in the 1950s. See Box-Jenkins signal estimation. This approach is based on harmonic analysis and filtering of signals in the frequency domain using the Fourier transform, and spectral density estimation, the development of which was significantly accelerated during World War II by mathematician Norbert Wiener. Electrical engineers Rudolf E. Kalman, Dennis Gabor and others for filtering signals from noise and predicting signal values at a certain point in time. See Kalman filter estimation theory, and digital signal processing segmentation, splitting a time series into a sequence of segments. It is often the case that a time series can be represented as a sequence of individual segments, each with its own characteristic properties. In time series segmentation, the goal is to identify the segment boundary points in the time series, and to characterize the dynamical properties associated with each segment. One can approach this problem using change point detection, or by modeling the time series as a more sophisticated system, such as a Markov jump linear system.